sun today and maybe this weekend even, which I was not expecting. The weather report seemed to be very different earlier this week. Uh, but yay, we'll take it. Okay, so in this section, in 3.1, and you guys are starting into 3.2, where we start looking at logarithms, which is the inverse equation of the exponentials. There's a few things that we have that are foundational to the exponentials. Let's talk about that first if I can get my pencil to work here. For an exponential equation, we define this as a to the x power, where a uh, cannot be 1. And the other thing is a has to be greater than 0. So the base, we're thinking of a as a number. We have some restrictions on that. When we talk about 1, if you think about 1 being raised to any power, it's always going to be equal to 1. It's one of those properties of 1. Um, and so it doesn't really make sense to have the base of an exponential function be 1. You're just going to get 1 as a result for any x. So it kind of breaks the uh, breaks the formula down in a sense. The other thing is 0 to any power, or in fact, if we have a as a negative number, let's say we have -2, like we have here. Well, we kind of have this, but any negative number, if I raise that to the first power, it's equal to itself. And then if you have another power like squared, so we're squaring a negative, that becomes +4. And we take it to the next whole number, 3, and now we're back down to -8. So you see it, we have this thing with the powers. When they're even, it becomes positive. When they're odd, uh, then they stay negative. So we don't take negative numbers. Basically, they have to be greater than 0. 0 is something we don't want, but we also don't want negative bases. So the base a there cannot be negative, which appears to be a contradiction here, right, in the problem. But notice the one detail that's different about the way this is written as opposed to what I'm doing down here. What is that one detail that's missing in the function which allows that negative to be there? Anybody? You can type your answer into the chat box. Here's a question. Am I violating the it cannot be negative, my base a cannot be negative, with the way this particular function is written? The answer is no. But why is that? Why am I okay with that negative being in front there? Here's where we would have a problem is if this was written like this. Here we would here we would have a problem. But the power there, the x, and that's what exponential functions are really about, is that our variable is in the exponent. Here, the variable, or the exponent that we have there, x-4, is only applying to the 2. It's not applying to the negative. The negative is just out front there. It's unaffected by the power. So the base itself is actually +2, which whenever we have a whole number, so a non-fractional, non-rational base, uh, we're going to get we're going to get exponential growth. The domain of an exponential function and the graph for exponential growth passes at 1 here. Hold on 1 second. All right. I know it's loud to my ears, so I know if it's coming over the speaker, my tongue is probably very loud over yours as well. And we're about the time where the mailman shows up, which is always quite the commotion. So when we have an A that's greater than 1, we have exponential growth. When A is a fraction, we have exponential decay. So here A is greater than 0. And by A, we're talking about the base of the exponential function, but less than 1. So it's in between 0 and 1. They both cross here at y equal to 1 because any base raised to a 0 power is equal to 1. So that's where it's crossing there. But of course, we can add things, subtract things from x as we have here, and we can add things out here, which will move it up and down, right? So we do have variety in where these guys intersect, but just the most basic function, if we're looking here, uh, is a raised to the x power. So when we look at this, what are the transformations? Well, actually, we'll get to that. Let's go ahead and just plug in some values here. Go ahead and type what you got for this f of -1. Go ahead and type it into the chat box. You can send it to me directly rather than to everyone. So you want to click on the blue box there, highlight Brock Leach, the host, not the co-host. Great. Close, really close there. Okay, great. I'm getting them in all forms, literally the decimal and then a mixed number and then an improper. Love it. Okay, good. Let's plug it in and work this out. Remember, you want to be careful with negatives and subtractions. Um, so what I have is -2 to the -1 minus 4, which you might think -3 because we tend to add, even though there's subtraction there, we see the 4, we see the -1, and really easy, but to mess those up. But remember, you can always add the opposite to kind of clarify. It's to the -5. So we have, and then we have +3. So this is -2 to the -5 +3. 2 to the -5 is 1 over 2 to the 5th. Right? When we have a negative exponent, just focusing on the negative exponent part. Sorry, this would be negative. Um, that moves it to the opposite part of the fraction. And then once it moves there, that exponent becomes positive again. So that's a 5, which is -1 over 32. 2 to the 5th power is 32. So this is equal to -1 over 32 plus 3, which if we take away 132s from a 3, that leaves me with 2 and 31 32s. And you can turn that into a mixed number. Several of you did. Becomes 95 over 32. If it's a decimal, I'm not sure. I can't remember if that's a repeating decimal, but it's about 2.97, somewhere around there, as if we round it. Great. Be careful about the rounding. We want to keep, if it's a terminating decimal, you want to keep all those decimals there. But if it keeps repeating with a pattern, at some point you have to round it. And in the problems that involve a lot of steps, you want to try to keep that as close to the original value as possible. Don't round too early. If your final answer is going to be several different steps in there, and then always look into the computer program to see how they want you to round it. You don't want to miss something because of a rounding issue. All right. So for f of 1, that's negative 2 to the 1 minus 4 plus 3. 1 minus 4 is negative 3. So we still have that negative power. Remember, we're not raising negative 2. We're only applying this to 2. So the negative just kind of hangs out here. This is negative 1/8 plus 3, which is equal to 2 and 7/8. Very good. So similar outcomes there. Any questions on what I did there? All right, let's move to the next one. Describe the transformation. So how is this particular function going to move around? What are the three different transformations that we have for this function? There's three different ones. See if you can isolate those and send them to me in the chat box. I'll give you a minute. The three transformations there for the graph. Excellent. Great. Really close. Remember that when we were doing this with parabolas and, well, polynomials in general, um, whatever was being done to the x was always the opposite of what we thought. And this carries over into this, carries over into exponential equations and logarithmic equations. So what we see is 4 is being subtracted from x, and then we're adding 3 to the exponential function negative 2 to the x minus 4. Right. So whatever that, when we plug in a value for x, we evaluate it. The first thing we're going to do is we're going to, since we're plugging in x, we're going to subtract 4. We're going to look at that power and the value, and then we're going to add 3. That addition of 3 is really affecting the value of the exponential part that we just carried out. So it raises it, or if we're subtracting it, it lowers it. So with the up and down part, it's always going to follow whatever we do. If we add 3, it's going to add 3 to whatever value we just got out of the exponential part. But when we're subtracting 4 from x, it actually ends up having the opposite effect on our graph. That moves it to the right 4 units, and then it moves everything up by 3. The negative out front here reflects it. So if it was going to be positive, now it's going to be negative. So that the result of that is reflecting it over the x-axis. So we do that first. We reflect it over the x-axis. Then we would move it forward to the right and then up 3. So this part means so this reflects over the x-axis. The negative does. This moves it to the right 4 because we're doing it to the x, so it's the opposite. And then the y part always follows the same sign. So up 3. Great. Those are our transformations. So what is our domain? Domain is what we're allowed to plug in for x. And when we talk about the domain of the general equation here, domain is what we're allowed to plug in. And as we look at the graph, you can see whether it's a exponential growth or exponential decay. We're using every x value along the line there. So domain for exponential equations goes negative infinity to infinity, and the range goes from 0 to infinity. Notice that it never goes below the x-axis there. Of course, if we're transforming it, moving it around, that might change, what we don't go below. So the domain for our exponential function is going to remain the same. It's negative infinity to positive infinity. There's nothing we're not allowed to plug into there. We're not going to get zeros under the denominator, and we're not going to get negatives under square roots. The range in this case, though, we need to think about the y. What's the lowest value you're going to get? And since we moved it up 3 units, the range here is going to, the lowest point that we'll never actually get to actually is -3 in this case because uh, it went up 3, but it's reflected. So we're reflecting it, we're moving it. No, I'm sorry. That's right. It's going to be +3. Actually, we kind of need to picture this. So if we reflect it, let's say that that negative wasn't there. We moved it to the right 4. That's not going to affect our domain, it's just going to affect the way it looks, right? So I'm going to draw kind of an imaginary y-axis here. Reflecting it is going to move it this way, right? So if it was exponential growth, it would look like this. We're reflecting it. We moved it to the right 3, so it's hitting 1 here and here. Except it's going to be hitting -1 because we're reflecting it. But now we've moved it up, uh, how many units? 3 units. 1, 2, 3. If this was kind of our new x-axis, it's going to look like this. So my range is actually, instead of going from 3 to infinity because it's below, it's going from -infinity all the way up to 3, not including 3, because of the reflection. So that was kind of a tricky one there. Excellent, excellent. Thank you, Elvis. Okay, let's move to the next one here. If we want to find the exponential function that contains these 2 points, -1 and 4, and then 1 and 16, there's 2 things that we need to find. We need to find C, the value out in front, and we need to figure out what the A value is. So plugging, I'm going to take the 1 and 16 here. 16 results when we have 1 here. And then we also have 4 resulting when A is -1. If we subtract these 2 functions, The resulting function would be 12. And can I subtract these? Yes, we can because we have the same bases, but we have different powers. So we cannot subtract those. What am I forgetting here? See, this would be 4 equals, I'm going to rewrite this. So this would be 4 equals C over A to the first power. Oh, we need to just do a substitution here. So let's solve for one of these variables. I'm going to solve for A. Since A to the 1 is just equal to A, if I divide both sides by C, A would be equal to 16 over C. Now I'm going to take this and plug this in for into the second equation. Might be better to solve, well, so if we plug that in, we have 4, come on, plugging this in for A, C, and then 16 over C to the minus 1. So this would give me, well, the minus 1 is going to flip that fraction. So I have 4 equals C over 16 to the 1 times C, which gives me C squared over 16 equals 4. So if we multiply both sides by 16, 16 times 4 is 64. This 16 cancels out. So I have C squared is equal to 16 times 4, which is 64. So taking the square root of both sides, C would be equal to 8. So plugging this C value into the original equation, I now have 16 is equal to 8 a to the 1 or a to the x. But plugging 1 in, we now can solve this for the a. And if I divide both sides by 8, I see a is equal to 2. So here I have my a value and I have my c value. Substitution is, how we can do that. We put in the values that we have. We use substitution from one equation to the other. So the function then would be f of x equals 8 times 2 to the x. Very good. Any questions on that? Okay, let's move to the four where we start talking about logarithms. Well, let's see if this will let me erase some of these that are gonna get in the way here. So some of the key things that we want to remember with logarithms, these are little rules you want to keep on a 3x5 note card, something that you can reference really quick, but just talking about what a logarithm function is, you kind of have to get past that whole boundary first. What is a logarithm function? Why do we have these? Well, logarithms are inverse functions of our exponential. So if we have a function, so they kind of undo each other. They take you from one point back. Any kind of inverse function will have a graph that goes across or be symmetrical to the y equal to x line. And so it's kind of like folding it across that line. What we end up with, instead of 0, 1, we then end up crossing at 1, 0, and we have something that looks like this. Another property of an inverse function is that their domain and ranges switch. So the domain for a logarithmic function goes from 0 to infinity rather than negative infinity to positive infinity. So we cannot plug negative numbers. Uh, has to stop at 0, unless of course we're transforming it, right? Then the we just can't have the negative outcome there. And the range goes from negative infinity to positive infinity. So we switch the domain and the range, and they switch it off there. While we're describing, for example, here a logarithm, we say log base 1/5 to the fifth equal to 1. That base word that we use is very telling because it's showing the connection between a logarithmic function and the exponential functions because they're inverse operations. We say base of 1/5 because in the exponential form, if we were to transform this, that ends up being the base of the exponential. So here, if we're transforming it from exponential to logarithm, I know that the base here, which is what we describe the part of an exponential equation, 49 would be my base, that ends up being the base of the logarithm. The answer here ends up being what we're taking the log of. And notice how the exponent becomes the solution to the log. And that's where this is helpful for us. When we're looking for a solution that's in an exponent, we can write it in a logarithmic form to find that exponential solution. So log base A of B equal to X. We take the base of the log. The answer is an exponent, so that becomes my X equal to B, which is what we're taking the log of. So remembering these relationships here, sometimes it's helpful to take something that's written in a logarithmic function, put it into an exponential form. A lot of times just doing that gives us the answer. In a log form, we're looking at the base and we're saying this base to what power results in B. So 1/5, oops, to this power, -1, is equal to 5. And here that we can see, yeah, that makes sense because if we're raising something to a negative power, that always flips a fraction. If we're doing a fraction or if we have a whole number there, it moves it to the denominator part. So yeah, this is probably, with our mentality right now, the um, easiest way for us to picture that. All right, let's describe the domain if we have shifted this. Very good, thank you. Well, we know that the domain uh, will change. If this is my original, we're going from 0 to infinity. Here we're subtracting 8 from x. And so that's going to give us a transformation, a horizontal transformation. Instead of my domain starting at 0, it's now going to start at 8. We're moving everything over 8 units. So my domain here is going to start at 8 and go to positive infinity. Notice that anything like 7, if I plug 7 into here, now I'm taking the log of something that's negative. 3, no matter what power I raise it to, is not going to result in something negative because we have a positive base there of 3. So, and with exponents, we can't have negative bases. So taking the log of something that's negative doesn't make sense for us because we can't raise a positive base. We can't take a positive base, raise it to a power, and end up with something that's negative. It's just that will never work. So anything less than 8 or equal to 8 um, will not work. Equal to 8 would be a problem because 8 minus 8 is 0. So we're saying 3 to what power results in 0? Well, 3 to even the 0 power results in 1. Anything raised to the 0 power is equal to 1. So I can't raise a positive base to any number and get 0. Like, it just, that'll never happen. It breaks our rules, the ones we originally established over here with our bases. They can't equal 1 and they have to be greater than 0. What is our range going to be here? Ranges are a little bit hard to decipher um, because we have to think about, we have to be able to visualize it. This is why the graph is important for you to be familiar with the types of graphs we get depending on what values are in there. But the range is talking about what our results are going to look like. Like if we plugged in from 8, not including 8, and all of those numbers, what kind of Y value outcomes are we going to see? Does anyone have a guess as to what the range is for this particular log function? And remember that when we go from uh, exponential to logarithmic and we look at their domain and ranges, remember they're inverse equations. So whatever was in the domain of the exponential function goes to the range of the logarithmic function. Yes. The range here, we know that the domain for the exponential function was negative infinity to positive infinity. So those are going to be the results I see in the range of my logarithmic. So the range is just going to be negative infinity to positive infinity. When we look at these y's, right, when we think of range, we're looking at what are the outcomes we're going to see on the y-axis, right? Those represent our ups and downs. Um, Even if I had shifted this up and down, the range is still going down over here to infinity. And it is going up to infinity over here. It just keeps going. It takes a long time for it to move up, but there is no horizontal axis here. There's no point at which that this part over here stops going up. So yes, it looks kind of like a horizontal asymptote, but it actually is not. It functions much the way that this does over here. Uh, Keeps on going. Oh, I'm sorry. This is the part over here. This is going up to infinity, and this is doing the same thing over here. It's going up to infinity as well, just at a very slow rate. Okay. Any questions before I erase all this stuff here? Let's go and talk about your homework. A couple other things that I wanted to mention. I did grade your graphing test, and I've been a little bit slow to get it back to you, but I'm after we get out today, I'm going to send it back to you in on Canvas. So I've got to turn them all into PDFs and then send them back to you. If for some reason you still have not taken that, then you need to come talk to me. A couple of you did because we had some issues that came up. Um, but if you missed the test that we tested in class last Friday, here we're at our next Friday. If you haven't talked to me about that and you haven't, uh, maybe you didn't know we were having a test that Friday, you're responsible to know. I had talked about it and leading up to it. We met last Friday for that specific purpose. And if there was issues that you were dealing with, you just need to talk to me about them so we can do a makeup on that if not. So stick around today if you're here and you haven't done that yet. I also went through, you probably noticed some improvements on your online test that we took last Friday. Uh, because I went through, as I always do with the online tests, and I looked at your answers compared to what the answers were. I gave some partial credit on a couple of problems. If you were marked off, but maybe you put a comma instead of a period on something, I awarded you full points back. So it just depended on the problem. There were some that I felt deserved some partial credit. So you probably saw a change and improvement in that score. As we're going through this, keep in mind the graphing. You want to practice doing some of these, getting familiar with how these look in general, how the transformations will change them, where any asymptotes might be. In the exponential, our asymptote is the x-axis, but of course, if we move it up or down, that's going to change. With the logarithmic, we have a vertical asymptote at the y-axis, and of course, figuring in transformations where that might move to. But otherwise, they don't really change a whole lot in terms of their structure. Okay, let's switch the viewing here. I'm going to take you to my desktop, and then let's go ahead and get into Pearson. We have 3.2 part one coming due today. So I'll start with that. Any questions you would like me to go over from 3.2 part one? Go ahead and type them into the chat box if you do. Any questions from 3.2 part one? Going once, going twice. We can go back to some of the other ones if you guys had questions over part two from 3.1 or part one from 3.1. Any questions? You guys feeling okay about this? Okay. All right. Well, if you haven't done these yet or you haven't started on these, and you do run into some questions, remember to post them on the discussion board. I'll be checking that throughout the day. Happy to weigh in if there are issues that you run into. You can always send me a message as well in Canvas. I'll be checking that all day. Um, cool. I'm gonna let you guys go. If there are no questions, or if you do have questions but you're feeling shy, please don't feel shy. Stick around, and I'm happy to uh, go over some with you who are left. Yeah, the logs are a little confusing at first, just because it's like, what does that mean? Um, think of them as a way for us to solve equations where we have an unknown value in the exponent. It's a way for us to solve equations where we're looking for a solution in an exponent. That's why we have them. Mood. Okay. Learn some stuff in the investments. I'm not understanding the mood comment. Does that mean you're in a mood?
It was just a rough assignment.
Oh, okay. On the last one, the last three.
Yeah, it was just a lot of decimals and yeah, it was a rough one.
Okay. Because somebody exactly knew what you meant. There was a heart there, unless you hearted yourself. Oh, okay, great. Yeah. All right. They can get a little complicated, especially trying to put them into your calculator. So there is the thing where looking at parentheses is really important. Um, and in a lot of those, you have that exponent part where you're multiplying two numbers. If and some calculators are better than others. If it doesn't put it, you should always put parentheses around that exponent. You probably figured out. If you're putting it in that way, a lot of times it's just easier to figure out what's the result of n times k. So you're not having to put another operation in there. You can just know what the result is. But yeah, that can be that can be challenging. Yes, you'll yeah. I would not recommend using the Apple calculator if you have any kind of smartphone, which I'm sure most of you, if not all of you, do. The Desmos, I believe it's called, is a great calculating graphing calculator. You can download Desmos. Let me make sure that's right. Desmos, yes. It's free, and it's even something that can be on your phone that you can use on a test. I can allow you to use that because most of the time we can't have people use smartphones on a test because you could be looking up stuff, right? You could be typing things into Chat GPT now. But what the Desmos allows you is to do a test mode where it locks your phone, and then you can show me how long your phone has been in Desmos mode. So, we've been taking a test for an hour, hour and a half. You can show me the time at the end of the test, and that tells me that that phone stayed locked in the calculator mode for that time period. That is a great piece of technology because that allows you not have to buy those expensive calculators just for tests. You can use that mode on your calculator, and it's free. I mean, there's probably some ads in there, but for the most part, it's free. And it's called DESMOS, Desmos. Don't use the calculator that comes on your iPhone. It is terrible, and now the assignment's passed too. But for future reference, you're going to have a lot more. It's going to be more straightforward using the Desmos calculator. It's good to have a backup in case you're at a coffee shop and your calculator you left at home. It'll perform in the same way as a graphing calculator. Well, have a great weekend, everybody. I'll be sticking around if you have any questions, you want to chat. Happy to help you out in any way I can. Have a great weekend. We'll see you guys next week.
Thank you. Have a great weekend.
Thank you.